The degree function for polynomial rings gives them a nice structure that allows us to conclude that they are, for instance, principal ideal domains and so forth and so on. We can generalize this idea slightly to other types of rings that have a function which behaves enough like the degree function that it can prove the same things about those rings. We call those rings Euclidean domains. Definition 142. A domain R is a Euclidean domain, which we often abbreviate as simply ED, if there exists a function n from the elements of R except 0. It might take 0 as an input, but it doesn't have to the natural numbers, called the Euclidean measure, or simply the measure of R, satisfying the following. Two conditions. For all non-zero elements x and y of R, we have that the measure of a product is product xy is greater than or equal to the measure of x, and for all elements x and y in R with y not equal to 0, there exist elements q and r in the ring R such that x is equal to qy plus r and r is equal to 0, or the norm of R is less than, the measure of R is less than the measure of y. So you'll notice that this condition 2 is essentially saying that the measure has to provide a version of a division algorithm, that every pair of elements x and y has to be able to be written as x equals qy plus r, where the measure of R is less than the measure of y. However, you'll note that contrary to the division algorithm for polynomial rings over a field, this Q and R do not necessarily need to be unique. They don't need to be unique in order for the ring R to be considered a Euclidean domain. Furthermore, the Euclidean measure of R is not unique. In particular, any multiple of a Euclidean measure by a non-negative integer is itself a Euclidean measure. So showing that a domain is a Euclidean domain means giving an example of such a measure that does this, and showing that a domain is not a Euclidean domain involves showing that there is no function that satisfies these properties. Of course, that second condition there is the more difficult one. To show that such a function does not exist is difficult because there are, of course, infinitely many different functions to consider. Now, we will see in a little bit that all Euclidean domains have certain other properties we're familiar with, and so we can use that to conclude that certain rings are not Euclidean domains. But the Euclidean domain condition is still fairly subtle. So let's look at some examples. The ring Z is a Euclidean domain. where we take the measure to be the absolute value. Let's check the conditions. For non-zero x and y in z, we have that the absolute value of y is at least 1. So we have that the absolute value of xy, we know that this is equal to the absolute value of x times the absolute value of y, which is greater than or equal to the absolute value of x, because the absolute value of y is at least 1. So we satisfy the first condition fairly well. Now the second condition, you need to be fairly precise about it. So for the second condition, let's let x and y be integers with y not equal to 0. We're going to consider a couple of cases. First of all, if y is greater than 0, then there exists some q such that q times y is less than or equal to x, which is less than q plus 1 times y. In fact, we can say exactly what this is. This q will be equal to x divided by y, rounded down to the nearest integer. So if y is positive, then we can always find a q that makes this happen. Letting r equal x minus qy, we have that, well, x is equal to qy plus r as we want. And also we have that r is greater than or equal to 0, and r equals x minus qy, which is less than q plus 1 times y minus qy, which is equal to y. So that means that the absolute value of r is equal to r, which is less than y, which is equal to the absolute value of y, because we're in the case where y is greater than 0. So we have that if we take r to be the difference between x and q times y, where q is the round down of x over y, then the absolute value of r is less than the absolute value of y. If y is less than 0, a similar argument holds. You can find the details in the notes. So that means that z, the integers, is a Euclidean domain. However, this also shows that the q and r in the Euclidean domain do not necessarily have to be unique. So q and r are not unique. So for instance, if we take x to be 18 and y to be 5, we could write down that 18 is equal to 5 times 3 plus 3, where q is 3 and r is 3. But we could also write down that 18 is equal to 5 times 4 plus -2, where q is 4 and r is -2. Both of these decompositions of x into qy plus r satisfy the condition that the measure of r is less than the measure of q. So in a Euclidean domain, we do not necessarily have uniqueness of the elements q and r, but we do have that such a q and r exist. It turns out that the uniqueness of such q and r is not really a very important part of the division algorithm from the point of view of studying the ring structure of such domains. Now, let's look at a slightly more complicated example. Finding Euclidean domains that aren't just the integers or polynomial rings over a field often require a bit of work. So let's take an example. So let's let R be the ring Z adjoin the square root of -2. And let's let the measure of an element a plus b times the square root of -2 be a squared plus 2b squared. Very similar to what we've been doing in our examples. We've been working with z adjoining the square root of -7. In this case, we'll do the norm of a plus b times the, or z adjoin the square root of -2. Now, we can show that for all x, the measure of x times y is equal to the measure of x times the measure of y. Also, if y is not equal to 0, then the measure of y has to be greater than or equal to 1. Because a and b are restricted to being integers, and so the smallest measure you could get out of something would be if a is 1 and b is 0, unless the element is the 0 element. So this tells us that the measure of x times y is equal to the measure of x times the measure of y, which is greater than or equal to the measure of x. Now, I should point out that in both of the situations that we've had so far, the function that we've used as our measure, absolute value just now, and our function n here, have had the property that n of xy is equal to n of x times n of y. This is not an uncommon thing to use, but it's not necessary. Notice that the condition for the Euclidean domain simply was that n of xy is greater than or equal to n of x when x and y are both non-zero. Okay, so that shows that we satisfy the first condition of, that n satisfies the first condition of being a Euclidean measure. Showing that the second condition holds is typically harder. Showing that we have some sort of division-like algorithm is typically harder. So in this case, let's do the following. Let's let x and y be in R with y not equal to 0. And let's let x be a plus b times the square root of -2. Y is c plus d times the square root of -2. We wish to find Q and R such that x is equal to q y plus r, and the measure of r is less than the measure of y, which is c squared plus 2d squared. So if q is equal to e plus f times the square root of -2, then we have that r is equal to x minus qy, so we can compute, we can express this in terms of a, b, c, d, e, and f. So in particular, we have that r is equal to x minus qy, which turns out to be, when you expand all this out, a minus ce plus 2df plus b minus cf minus de times the square root of -2. And so essentially what we want to do in order to show that this function n is a Euclidean measure for R is we want to see that we can choose an e and an f so that the norm of this R function is small. Another way of thinking about it is that we want to find an e and f that makes this expression as close to 0 as we can. Looking at this, we've got r equals qy, x minus qy, which is a minus ce plus 2df plus b minus cf minus de times the square root of negative 2. I want to write this in the following way: a plus b times the square root of negative 2 minus e times c minus d times the square root of negative 2 minus f times negative 2d plus c times the square root of negative 2. So because we're trying to choose E and F, I want to rearrange this in such a way that we've got E and F factored out of their respective pieces. So we want to find an E and an F that bring these, the sum of these two pieces as close to the value of a plus b square root of negative 2 as possible. So one way that we can think about this is in terms of linear algebra. We're trying to find integers e and f in Z so that e times the vector this should be a plus d, e times cd plus f times negative 2dc is close to the vector ab, where here I'm using vectors where the first component is supposed to basically represent the first part of the number, and d is, the second component here is supposed to represent the coefficient of the square root of negative 2. Now we can note that the vectors CD and negative 2DC are linearly independent. In two-dimensional real vector space. And we can see that, the easiest way to see that is by checking that if we put these vectors into a matrix, then their determinant is non-zero. So the determinant of the matrix with column CD and negative 2D is equal to c squared plus 2d squared, which is the norm of y. And in particular, that means that it's not 0 because y is not 0. Now, because these two vectors are linearly independent in two-dimensional real vector space, that means that they form a basis. So the vectors c comma d and negative 2d comma c form a basis of R2. So that means that there are elements E prime and F prime in R, so that E prime times CD, C comma D, plus F prime times negative 2D comma C is equal to the vector A comma B. Is exactly equal. We're trying to find integer E and F that make the linear combination E times CD plus F times negative 2DC close to the vector AB. Here we can find real numbers that will make them exactly equal the vector AB. So now we can let E be the closest integer to E prime and F the closest integer to F prime. And then we can look at what the norm of R is. So now we have that the norm of R is equal to a minus CE plus 2df squared plus 2 times b minus CF minus DE squared, which we're going to replace a with e prime c plus e prime c minus 2df prime. That's coming from the from expressing the vector, the element A as this combination involving e prime and f prime. And then B will be C f prime plus D E prime, and then minus CF minus DE squared. So this is just using this equality right here. A is equal to e prime c plus f prime times negative 2d. B is equal to e prime d plus f prime times c. So now we can, that's squared. So now we can write this as c times e prime minus e minus 2d times f prime minus f, all that squared, plus 2 times d times e prime minus e plus c times f prime minus f squared. And then expanding all this out, we're going to get quite a bit of cancellation. So we get c squared times e prime minus e minus 4dc e prime minus e f prime minus f plus 4d squared times f prime minus f squared. Missed a squared right there. Plus, expanding out the second term, we'll have 2d squared e prime minus e squared plus 4cd e prime minus e f prime minus f, and then plus 2c squared times f prime minus f squared. We have that the second and fifth terms cancel, and then we can factor c squared plus 2d squared out of the two terms with e prime minus e squared, and then 2 times 4d times c squared plus 2d squared times f prime minus f squared. So we wind up with c squared plus 2d squared times e prime minus e squared plus 2 times f prime minus f squared. So this is the norm of R when we choose our e and our f in the way that we defined, and defined R to be x minus y times q. Now, notice that c squared plus 2d squared is exactly equal to the norm of y. E minus e prime is at most 1/2. F prime minus f is at most 1/2 because f was chosen to be the closest integer to f prime, e was chosen to be the closest integer to e prime. And so we get that this is equal to the norm of y times 3/4. In particular, this is strictly less than the norm of y. So that means that we can find integers e and f that make the norm of r less than the norm of y. So setting q to be e plus f square root of negative 2, and r to be x minus qy, we have that the norm of r is less than the norm of y, which proves that this function n is a Euclidean measure for the ring R, and therefore the ring R is a Euclidean domain. All right, let's do another similar example to this one. Let's let R rather be the ring Z adjoin the square root of negative 3. And let's let n of an element a plus b square root of negative 3 be a squared plus 3b squared, just like we had before, just replacing the 2 with a 3. This is a natural function, and just like before, we have that the norm of xy is equal to the norm of x times the norm of y, which is greater than or equal to the norm of x if y is not equal to 0. So it satisfies the first condition of being a Euclidean measure. However, it doesn't satisfy the second condition. Let's see why. Let's let x be the element negative 1 plus the square root of negative 3, and y be the element 1 plus the square root of negative 3 in the ring R. And let's suppose that we have some element q in the ring which has the form a plus b times the square root of negative 3. Now, if this n were a Euclidean measure, then there would have to be some a and b such that the measure of x minus qy was less than the norm of y. So the question is, can we find a and b such that the norm of x minus qy is less than the norm of y, which is 4? Let's see that we can't. So the norm of x minus qy is going to be equal to the norm of, if we take x minus qy, multiply all this out, we get negative 1 minus a plus 3b plus 1 minus a minus b times the square root of negative 3. Now, the norm of this is negative 1 minus a plus 3b squared plus 3 times 1 minus a minus b squared. And when you expand this out, this cancel, this becomes 4 minus 4a minus 12b plus 4a squared plus 12b squared. And if we bring the a pieces and b pieces together and factor out, we get that this is 4 plus 4a times a minus 1 plus 12b times b minus 1. Now, because the a and the b are restricted to being integers, we have that this term 4a times a minus 1 is greater than or equal to 0. If a is negative 1 or less, then a and a minus 1 are both negative, so their product is positive. If a is at least 2, then a and a minus 1 are both positive, and so their product is positive. And if a is equal to either 0 or 1, then the product a times a minus 1 is 0. So in any case, a times a minus 1 is greater than or equal to 0. And similarly for b times b minus 1. So no matter what, this norm of 4 plus the norm of x minus qy is greater than or equal to 4, which is, the norm of y. So the answer to the question, can we find AB such that the norm of x minus qy is less than the norm of y? The answer is no. So this means that the function n is not a Euclidean measure. For R. Now, of course, this is not enough to conclude that the ring R is not a Euclidean domain, because there could conceivably be some other function which does satisfy the conditions of being a Euclidean domain. In order to understand when things are Euclidean domains or not, we can use the following theorem, which tells us that Euclidean domains are related to other domains that we're familiar with. Let's look at Theorem 143. It says, if R is a Euclidean domain, then R is a principal ideal domain. So this theorem tells us that Euclidean domains are actually fairly uncommon. Having a Euclidean measure is a very strong condition. If you're a Euclidean domain, then you're a principal ideal domain. Principal ideal domains are fairly rare in the space of all domains. And they have lots of nice properties. Before getting to the proof, I want to mention Corollary 144, which says that if R is a Euclidean domain, then R is a unique factorization domain. And we know this because we know that all principal ideal domains are unique factorization domains. So in particular, we have that the following rings are not Euclidean domains. We have that the polynomial rings over the integers are not a Euclidean domain because they're not a principal ideal domain. They are a UFD, but they're not a principal ideal domain. We have that the ring Z adjoin -7, which we've looked at throughout this this section, is not a Euclidean domain because it's not even a unique factorization domain. And in fact, we can use very similar sorts of arguments to show that the ring that we just looked at, Z adjoin -3, is also not a principal ideal domain. It's not a unique factorization domain, and so it's not a Euclidean domain. So the easiest way to see that a ring is not a Euclidean domain is not to show that there doesn't exist a Euclidean measure, but to show that it's not a principal ideal domain. Unfortunately, this doesn't completely solve the problem because there do exist principal ideal domains which are not Euclidean domains, although their construction is a little more complicated than we're able to get into here. All right, so let's look at the proof of Theorem 143. Now, this is very similar to the proof that polynomial rings over a field are principal ideal domains, and that's because the whole point of the Euclidean domain is generalizing that idea. So let's let R be a Euclidean domain with Euclidean measure n, and let's let I, subset of R, be an ideal. Now, if I is the zero ideal, then I is clearly principal. So let's suppose that I is not the zero ideal, which means that in particular it contains non-zero elements. Now, let's let A in I be an element of minimal measure. it's going to turn out that this A is going to be a generator of I. So we claim that I is can be generated by just the element A, which shows that I is principal. So to do that, let's note that we clearly have that the ideal generated by A is contained in I because A is an element of I. So let's let B be an element of I. Since N is a Euclidean measure, there exist Q and R inside the ring R, such that B is equal to AQ plus R, and the norm of, and R is equal to 0, or the measure of R is less than the measure of A. So this is just by definition. Now, note that R is equal to B minus AQ, which belongs to I. Since B belongs to the ideal I and AQ belongs to the ideal I. So, it cannot be the case that the measure of R is less than the measure of A. That's because we specifically chose A to be an element of minimal measure inside the ideal I. So anything else inside I cannot have a smaller measure. So that's not the only option. The other option that we had is that R is equal to 0. So B is equal to AQ. And I'm going to have to write the conclusion on the next page. Since B is equal to AQ, B is contained in the ideal generated by A. Therefore, since this holds for any B in I, this tells us that I is contained in the ideal generated by I, and so I is equal to the ideal generated by A. Hence, R is a principal ideal domain. So this shows that in any Euclidean domain, any ideal is principal, and you can find a generator of it by taking a non-zero element of I with minimal measure. All right, and so we have some corollaries to it that we've already mentioned. One of the last things I want to mention here is that any field is a Euclidean domain, and sort of trivially, for any function n. And this is because if A and B are in a field F, and B is not equal to 0, then we can always write A as AB inverse times B plus 0. So we can always take B, we can always take Q to be AB inverse and R to be 0. Oh, I shouldn't say any function n. I should say basically any function n, because you still need the first condition of the Euclidean domain to hold. Any constant function will certainly work here. So any field is a Euclidean domain, and you can take any function you like, basically, for any function you like for it. Now that we've defined Euclidean domains, that finishes up, at least for now, the collection of different kinds of rings that we consider. Notice that a lot of the rings that we consider can be put into a string of containments. What we just showed is that all fields are Euclidean domains. So all fields are Euclidean domains, and this containment is strict because we have examples of Euclidean domains that are not fields, such as polynomial rings over fields. Polynomial rings are all principal ideal domains. Now, this containment is strict, but as I said, that construction is a little complex, and it actually took a while from the definitions of these types of rings to show that. Now, every principal ideal domain is a unique factorization domain, but we know that that's that they aren't equal because, for instance, unique factorization domains contain the polynomial rings over the integers. Now, unique factorization domains are, of course, subsets of the set of all domains, but it's a strict subset because there are domains which are not unique factorization domains, such as our ring Z adjoins square root -7 that we've worked with. All domains are contained in the set of commutative rings with unity, but not every commutative ring with unity is a domain. It's very easy to find ones that aren't. And the commutative rings with unity are just a proper subset of the set of all rings. So these are some of the most important classes of rings that we work with. And the further left you go, the more rigid the structure of the ring gets. The more we know about the structure of the ring, and in some ways, the more things that you can prove. But as you move to the right, you get much, much larger classes. If you compare all domains to all unique factorization domains, there are so many more domains that aren't unique factorization domains, and so many more commutative rings with unity that aren't domains. And so these things grow significantly as you move to the right. Different mathematicians fall different places essentially along this line on where they tend to study. Different people who study algebra. Basically what happens is if you study classes of rings that are further towards the left, you have lots and lots of theorems to work with. If you study Euclidean domains, you've got this Euclidean measure that gives you lots of things. You know that everything that you work with is a principal ideal domain and a UFD, and et cetera, et cetera, et cetera, et cetera. And so there are lots of tools that you have in your disposal to prove things, but you're proving things about a narrower class of rings. On the other hand, the further to the right you go, you're proving statements about more general rings, but you have much less to work with. If you study commutative rings with unity, well, then you don't know whether or not you have zero divisors or not. You don't necessarily have unique factorization, and so you need to work harder to get statements that apply to all commutative rings with unity, because you don't have the structure that for your set of rings you study that people who work further to the left do. But you're studying a larger class of rings. So different people fall at different locations here. In my research, I focus on rings like this, commutative rings with unity, but there are plenty of people who study classes of rings that lie all along this spectrum.